Good afternoon everyone. Today we'll be looking at designing and simulating a control system for inverted pendulum. So what is an inverted pendulum? An inverted pendulum is essentially a structure that is top heavy and is inherently unstable. Take for example this bottle. If I invert it, it's top heavy and it's inherently unstable. As you can see, I would constantly need to move my hand in order to balance, to keep this inverted bottle stable. Essentially, it's like a control system, which is what we are looking to design and simulate today. So here is a diagram of the inverted pendulum with mass MP. It's connected to a massless rod of length L, and theta is just the angle of the pendulum from the y-axis. I'll talk a bit about the center of gravity of the pendulum in just the next slide. So this pendulum is connected to a cart with a pin joint, and this cart has mass mc. So when subjected to a force F, this cart would move forward with distance x or acceleration x double dot. So therefore, the center of gravity of the pendulum given by location xp and yp is as xp equals to x plus L sine theta and yp is L cos theta. So we would first need to understand how this pendulum moves when subjected to a force F. Essentially, we will need to apply the equations of motion to understand this system before we could apply a control system to control and stabilize this pendulum. So to begin, we'll first look at a free body diagram. Here is the free body diagram. Recall that there's a pin joint connecting the cart to the pendulum, so therefore there are two forces, equal and opposite. And in this instance, I've ignored friction just for simplicity. Now looking at the individual free body diagram for the cart on the left and the pendulum on the right. And we'll first look at the pendulum using equation of motion for rigid body motion. Summation of force equals to mass times acceleration in x and y direction, and summation of moment equals to I times alpha, where I is the moment of inertia and alpha is the angular acceleration. So in the x direction, we have force equals to mass times acceleration, where acceleration is just the double derivative of the position of the center of gravity for the pendulum. And we end up with equation 1. And likewise, in the y direction, summation of force equals to mass times acceleration in y direction. We end up with equation 2. And applying the third equation, summation of moment equals to I times alpha. Using clockwise as our positive convention, we end up with equation 3. So what can we do with these three equations? We could obviously substitute equation 2 into 3 because they are both Fv present. And I could also substitute equation 1, Fh, into equation 3. So by doing so, substituting 1 and 2 into 3, I end up with equation 4. So now looking at the cart, taking summation moment in the x force equal to mass times acceleration in x direction. Here we have equation 5 here. Once again, we see this Fh term, and we could substitute equation 1 into Fh, and we end up with equation 6. So using small angle approximation, we know, or we want theta to be small because we would want the pendulum to not oscillate too far from the y-axis. So therefore, sine theta is theta, cos theta is 1, and theta dot, which is angular velocity, is small. Square a small number is even smaller, so therefore we could approximate that to be 0. So with this small angle approximation, we could substitute into equation 6 and equation 4 to obtain these equations up here. So for equation 4, using small angle approximation, I end up with equation 7, and for equation 6, using small angle approximation, I will end up with equation 8. So what I do really want is to know how theta changes for a given force. And to do that, we need the transfer function. We are going to combine equations 7 and 8 and then apply Laplace transform to it. So here is the transfer function, which essentially tells me for a given input, Fs, I would have a given output theta, which is the position of the pendulum. So now with this transfer function, I could use MATLAB to design a control system. But before that, we should define some design criteria. I want the settling time to be less than 5 seconds. I want theta to oscillate less than 0.1 radians. I want to limit the movement to be less than 0.1 radians. And the steady state error should be less than 0.005 radians. Okay, so now moving on to MATLAB. So right here on the right, I've arbitrarily chosen some values for the system. Mass of card, mass of pendulum, moment of inertia, gravity is 9.8. The length of the pendulum, the length of the massless rod is 0.5. And this is transfer function that we derived. So running this M script, we end up with this transfer function with values. And we're going to implement this into Simulink to design our control system. And here is the Simulink model. Right here is the transfer function, or the plant if you like. If we go into the plant, you will see the numerator coefficients 0.655 corresponds to the 0.655 over here for the numerator. Starting with the highest power with s to the power of 1, followed by s to the power of 0. Because there's no constant, therefore it's 0. Likewise for the denominator, we start with the highest power, which is s to the power of 3, and that gives us a constant from 1.716, 1.716. S to the power of 2 is 0, so it's 0, followed by negative 38.51, and no constant, 0. I'm going to use a PID controller to control this system. So a PID controller is a proportional, integral, and derivative controller. There are many other control systems that you could apply, or we could apply, but I've chosen the PID for this instance here. Okay, so in this control system, I could change P, I, and D individually to see the effect on the control system. And I'm going to subject this control system to two different forces, an impulse and a step. So this is an impulse, and if I were to run this control system with just a proportional value of 10, so this is the impulse, and here is the position of the pendulum. X-axis is time, and y-axis is radians. So you could see that as time increases, the position of the pendulum increases and is unstable. So we could increase P to try to make it stable. Let's say 120. And if we run it, okay, so now we see that the system is stable, but unfortunately it oscillates, which is not really what we want. So to remove this oscillation, or to reduce these oscillations, we could add in some value of derivative, let's say 10, and we run the system again. Okay, so this time around, it seems to be stable, and it achieves our design criteria of less than 5 seconds of settling time and steady state error of less than 0.05. So next, let's try using a step input. Okay, when we apply a step input, it seems to be stable, but unfortunately, the steady state error is closer to 0.02, which is not what we want. And to remove steady state error, we could put in some values of I, the integral. Let's say value of 10, and run it. Okay, so we could start to see the steady state error decreases, but it's still not within the settling time of 5 seconds as what we have specified. So we could increase I slightly and try running it again. So this time around, it seems to be stable with steady state error of close to 0 and less than 5 seconds for settling time. So just switching back to impulse to check and ensure that it works as well. So it seems to work with settling time less than 5 and 0 steady state error. So there you have it. a control system for an inverted pendulum. Thank you.